then, okay, thank you, Ryan. Please
Okay.
go ahead.
Okay. Well, thank you, JP. I want to just start off by thanking you for the opportunity to speak at this workshop again / school. This is really, I think, a huge service to the community, and I really appreciate that you put it on every year. And it's really one of my favorite things. I wish I could have been there in person, but I'm teaching and it just was too much. So in any case, glad to see everyone, even though on my screen, everyone's little tiny dots. I'll still try to see who's there. What I'm going to talk about today is sort of my big picture perspective.
Oops.
Is that I'll cover three basic categories of information, and hopefully I'll make it all the way through. The first thing is that I want to give a very quick comment on what I think about how we can go about choosing what to grow, right? And a theme that I think everyone has encountered is that the chemical structural phase space is so unbelievably large that we can't just make brute force excursions in it. We have to have some sort of idea about how to do that. So I'll give you my 2 cents on that. And I think it's almost certainly the case that many of the other speakers are talking about exactly that, or at least their perspective on that. Okay, so once we choose something that's worth growing, then of course we have to actually make it. And that's where the rubber hits the road a lot of the time. And in order to reasonably make progress, we want to have some sort of basic skills. And so what I want to do is to introduce some of the parts of that I think are important. And in particular, I want to talk about binary phase diagrams, which ultimately go back to our introductory thermodynamics and statistical mechanics class. But I promise I won't do any math. And I won't even really go that deep on that part. Okay, and then once we have that in mind, and we know certain things about our precursors and combinations of elements and how they're going to behave, then we can make a rational decision about what synthesis methods are actually going to be useful. And I'll say something here about some of my favorites and how to implement them, maybe some tricks along the way. All right, so just another just fair warning. My internet connection this morning has been a little bit wonky. So if I do freeze up, I won't know it. But when I come back, maybe jump in and let me know, and I can go back to wherever it froze up. All right. So here we go. And do I sound okay, JP?
Yeah, everybody can hear Brian? Yep.
Okay. Okay, great. So here we go. So first of all, I just want to say something broad about quantum materials. Of course, by now, the term quantum materials is actually a very bad definition. It's so broad, and in some sense, it's like everything's a quantum material. You don't just get to turn quantum mechanics off. But what I think is exciting about quantum materials is that they're an environment where we can see the emergence of really a wide variety of different exotic electronic, spin, structural states, right? This can be things like superconductors, complex magnets. I think I saw that some people are talking about altermagnets at the workshop, so on and so forth. And the bottom line here is that we get these behaviors when we mix together some sort of fundamentally quantum properties, like the wave-like character of electrons in solids, their quantum spins, and then their structural and orbital degrees of freedom, right? And these seemingly simple ingredients give us this huge explosion of different behaviors. And to me, that's why we would be interested in quantum materials. The other thing that I like to say about it is that unlike other physicists or chemists or material scientists, who are kind of studying just the one universe that we live in, what's neat about quantum materials is that for the electrons that live inside of them, it's as though each different material is its own universe, right? So we essentially have an unlimited number of universes to look at. I think that's pretty exciting. All right. So we want to find more and more of these, not just because they show really interesting behaviors, but also because some of those behaviors are actually useful for things. But we're immediately confronted with this almost intractable problem that if you have the entire periodic table and you think about combinations of elements and all the different structures they can go into, and then add into that the fact that we need to chemically substitute things a lot of the times, for example, in the cuprates, to get high temperature superconductivity, the phase space is just essentially infinite, right? We can't make brute force excursions here. And so we need to have some sort of boundary conditions. So the boundary conditions that I think are minimally important, or they're sort of the minimal boundary conditions, but they're not sufficient, are that we need to have a real familiarity with the fundamental degrees of freedom that are available in the periodic table. You know, different sets of elements give different properties. And this will boil down to lattice, electron, spin, and, oh, I said lattice twice. I meant spin orbit. Okay, so these are kind of our degrees of freedom, and we want to know where to find them. In order to do that, we have to develop this sort of deep knowledge of connections between the chemical structural phase space and electronic and magnetic trends. And I'll return to that in just a second to give a summary of how I think you can do that. Okay, so what this can lead to is a process whereby you actually do go sifting through the chemical structural phase space, but with the intent of sort of achieving guided serendipity, right? We want to use these insights to guide us to the sorts of materials that matter. The other thing that is unavoidable, but it's very hard to know when it matters, is quality, right? So disorder in materials can matter a lot. For example, I think people in this audience have probably heard all about uranium tellurium-2. This is a wonderful example where the amount of disorder in the system fundamentally decides the ground state, whether or not it'll be a superconductor. But there's still other materials like cuprates where they're sort of intrinsically disordered. You dope them to achieve the superconductivity. And so how would you ever know in which case, you know, disorder matters? All right, so these are sort of the frame that we have to think about. All right, a different way of putting all this is that in order to make progress, we have to make an interdisciplinary effort where physics, chemistry, and material science, and now other things like big data or maybe AI. I know there are a lot of debates about whether or not that will actually matter, and probably still other disciplines, right? All of these things have to be harnessed, and we have to try to make them work together in harmony. That's the way that we can achieve guided serendipity. All right, now I just want to give one quick example of how this has happened historically, because it's really one of my favorite examples, but this is a stand-in for almost any other you know, set of phenomena that you could think of. And so when we set out to try to, you know, create things, we kind of need to zero in on a degree of freedom. And a good example of that is seen in the history of what has happened with rare earth compounds, right? This stretches back to the 1960s and even before, and I absolutely won't capture the entire history, but one thing that's true is that starting from the beginning, a part of the interest in rare earth elements was to develop better magnets, right? That's choosing a degree of freedom and pursuing it. And of course, there have been thousands and thousands of rare earth compounds that exhibit magnetism. Some important outcomes of that effort are shown here, where we know that samarium cobalt-5 and then neodymium iron boride are sort of the apex of finding anisotropic ferromagnets that work at reasonably high temperatures, right? So choosing a vector and pursuing it led to actual outcomes that we intended. But that's not really the most important part of this story, because along the way, there was this huge development of other unexpected things, right? And this includes things like realizing that for some F elements, like those based on cerium, ytterbium, or uranium, and some others, you can have mixing between the F and conduction electron states, giving you Kondo lattices and heavy fermion behavior. There's a whole bunch of unconventional superconductors that would not have been conceived of prior to their discovery. Recent examples are like uranium, tellurium-2, cerium, rhodium-2, arsenic-2, and then still other exotic electronic and magnetic states that people are still working on. One of my favorites is uranium, ruthenium-2, silicon-2, which exhibits the strange hidden order state at 17.5 Kelvin. All right, so the point here is that by choosing a rational direction and then starting to sift, you give an opportunity for serendipity to step in and start to do something. And that's how we've done things historically. Ideally, we'd find a way to accelerate this process, but I myself don't think that we really know how to do that yet. All right, one last comment on this, and this is just the issue of sample quality, which does matter, right? We know that in the development of transistors, it really wasn't until very clean germanium was made that working transistors started to appear. Okay, that's a great example. In gallium arsenide, in quantum Hall effect, having really high quality samples mattered a lot. And then most recently, seeing superconductivity in uranium tellurium-2. Probably most people know this, but the earliest reports that I know of on this compound go back to 2006. These were relatively low quality samples that were produced in a tellurium flux. I'll talk more about flux growth in a few minutes. And as you can see, I don't know if you can see my pointer, but this upper curve here in gray has a large residual resistivity and no superconductivity. A little bit later, Sheng Ran, JP, Nick Butch, and some others made the same material using iodine vapor transport. This resulted in higher quality samples, as can be seen through this lower residual resistivity and the appearance of superconductivity. Right, so in this case, it clearly mattered. So we have to keep this concept of sample quality in mind, but what's difficult is knowing really when does it matter or when will it matter. I think that's a question that I don't know how to answer before I do the experiment. Okay, so that's basically it for what I'm going to say about how we're going to choose what to grow. So now let's suppose that we have made a decision about what to grow, and we need to go and do it. So before we do it, I think it's critically important to do some thinking, right? There's something that Brian Sales always says, and it's something along the lines of a few days in the library can save you months in the lab. And I cannot tell you how many times I've ignored that advice and I've spent months in the lab and then done something that I didn't need to do or done something unsuccessful. So I think it's really important to heed that advice. And a first step in doing that is to have the right references. So I want to bring to your attention these 3 books, and there are others, but these are really valuable. So this book by Pamplin, if you're going to do any sort of bulk crystal synthesis, you should consult this book. Unfortunately, it's out of print, but you can find it on Amazon pretty easily. Maybe you can get your PI to buy it for the lab. Another one that's really great, it's from the FQM conference, is this one edited by Paglione, Butch, and Rodriguez. I highly recommend that. And not just because I published one of the chapters. And then finally, this book in the middle is very valuable because it will tell you something actually real about how dangerous the things you are, sort of the chemical properties. How dangerous are the chemicals? And the reason that I highlight this is just that, I think everyone is aware of materials safety data sheets and that they come with whatever elements or compounds that you buy. They're valuable. You should read them. But if you really take them at face value, you might come away with the feeling that everything that you might have in the lab is extremely dangerous. And I'll just give one example. I just bought some sand. I needed some sand, like high quality sand. I bought it from Fisher Scientific, I think. It came with an MSDS sheet. I read it, and boy, did that MSDS sheet sound like it was dangerous. All right. So in order to really know whether or not something is dangerous and in what way, it's a good idea to have resources like this And then I would also just really recommend that if you embark on a new synthesis process, talk to some experts in advance, right? There are people at this conference and others who are not here now, and most of them are going to be very happy to talk with you and give some advice on what to do. All right, so that's my first piece of advice is do the reading before you try to do something in the lab. Okay, now I want to just briefly return to this idea of thinking about the connections between chemical structural degrees of freedom and electronic magnetic degrees of freedom. And just point out that when you look at the periodic table, you can kind of think of it as a supermarket for different types of properties. Right? And so what do I mean by that? Well, it's something like this. When you go through the periodic table, you can realize that different parts of it are going to give you really distinct features. And I won't read this whole thing, but I'll just point out that if we go on the left-hand side, for example, and think about alkaline metals and alkaline earths, what you would get here is perhaps tuning of the unit cell size, going down the column, or band filling, going from left to right. That's going to be completely different from what you would find amongst transition metals, where in the first row, you have a good chance of finding magnetism. And then also throughout here, you can tune the density of states pretty easily. And then, of course, that even will be contrasted completely with what you'd find in the P block. Right? So as you set out to make things, you do want to think about what different degrees of freedom are you getting from these different types of elements. Okay, but even as you do that, that's kind of the physicist hat that you can wear. You should also put on the chemistry hat and think about what do you get, or what are the properties of these different groups of elements. So here I'll go through quickly. We mentioned the alkali metals and alkaline earths. Here, almost universally, you're going to find that they're pretty air sensitive, but they're also easy to melt. Right? So in other words, handling them on the bench top might be challenging, but once you get them in the furnace in some sort of enclosure, not such a difficult job. On the other hand, transition metals tend to be not so air sensitive, although of course iron or manganese or nickel will oxidize over a long period of time, but they're substantially harder to melt. And then amongst these, embedded in them are the refractory metals, things like rhenium and tungsten and molybdenum that have really high melting temperatures. Elsewhere, in these light elements, boron and carbon, they're super abundant, but they're also a giant pain because they don't like to melt and they don't like to dissolve into other things. So if you want to deal with these elements, you have to have a strategy going into it. Okay, what else? P-block elements, a lot of them have high vapor pressures. Really want to advise you to consult your vapor pressure curves. That can help you to avoid causing reactions to explode. And then many of these are poisonous as well. Some other P-blocks are a little bit better in terms of their vapor pressure, but you might find certain examples like thallium that are really very poisonous. So watch out for that as well. Okay, and then finally, lanthanides and actinides, they have their own special set of issues that you need to consider. All right, so my main message here is that as a physicist, you're thinking about electronic and magnetic degrees of freedom. And as a chemist, you're thinking about these other, and material scientists, you're thinking about these other sort of physical properties that have to be taken into consideration. Okay, so that's the ground rules. But what we're going to find out is that when we start mixing elements together, even in binaries, the rules change, and they change a lot and pretty quickly. So now I'm going to switch gears and start talking about binary phases of elements. And here, our bottom line question sort of is, how do elements interact with each other? And an even more fundamental way of putting that is, what is the thermodynamics, right, of having pairs of electrons? And if you don't remember Gibbs free energy from thermodynamics, now is the time when it comes back. But I won't lean too heavily on it. But I just want you to have in mind that this is where the Gibbs free energy becomes relevant. All right, so what can we say? So when we think about binary combinations of elements, what we need to go to are these chemical phase diagrams. And what's shown here is a generic one. By the way, this is taken from a really nice paper by Paul Canfield. The reference is included at the bottom here. I highly recommend reading it and rereading it and rereading it. It's a very valuable paper. Anyways, what's shown here is just a generic binary phase diagram. For real combinations of elements, there was a tremendous amount of work that was done in the 20th century looking into different combinations. This work was done in the US, in Europe, in Eastern Europe, in Russia, and we have in other places too, I'm sure, Japan. And we have a pretty comprehensive knowledge of what these binary phase diagrams look like. They were derived experimentally, but now they can be calculated as well. And so these are like an incredible trove of information when you're thinking about how to plan a growth. But in order to use them effectively, you need to know what the various regions in them are and what they mean. So what I'll do is go through this generic binary phase diagram as a stand-in, and then I'll show a real binary phase diagram. Okay, so what do we have here? What's shown is between elements A and B. On the y-axis, we have temperature, and on the x-axis, we have the atomic mixing composition. Okay, and there's a whole bunch of different features in here. The first one to notice is this non-monotonic line that separates the high temperature from the low temperature region. In high temperatures, this is the liquid phase, and at low temperatures, it's the solid phase. But there's more to say about it than that. And one of the first things to say about it is that you'll notice that there are these, vertical lines. And actually, there's two different types of vertical lines. The first of these is one that connects all the way through the solid phase and then into the liquid. And what this is called is a congruently melting phase. And it means that there's a phase that's a combination of A and B that has its own distinct crystalline structure. Right? It's a phase of matter. And it's connected to the melt directly. Right? So this means that if I can heat a combination of A and B to sufficiently high temperatures, and I'm going to ignore what this temperature might be for now, let's just say we can reach it, then if I cool back down, I will enter this AB phase. And regarding crystal growth, and I will come back to this again later, the only real question is, as we cross this boundary, can we control the nucleation of grains? And there are many, many ways that have been developed to do that. So I'll say more about that in a few minutes, right? But in any case, this is a congruently melting phase. There's another type of vertical line, and this is an incongruently melting phase. This is also called a phase that undergoes paratectic decomposition. So what does this mean? In this case, what it means is that I could take elements A and B, combine them in this ratio of 2 to 1, and get a compound, right? A distinct phase. And if I took A and B, maybe as powders, like, mix them up, put them in a press, and reacted them, that reaction would drive towards this thermodynamically stable phase. But because I'm accessing it from the solid state, it would inevitably produce a polycrystal, right? Where we have grains of the thing that are randomly oriented with respect to each other. Okay, but I could make it. And then if I were to heat this thing up, it would remain in that phase up to a point until I reach this horizontal line, okay? And above this line, it begins to decompose. Let's take it from a different perspective. Let's say that I had this composition, and I went all the way up into the liquid phase. And then I crossed this phase boundary. What would happen is that some of this would solidify, some parts of it would remain in the liquid phase. There's a coexistence of liquid and solid here. You can understand that by considering the relative Gibbs free energies of the solids and the liquids within this region. And by the way, if you really want to get into the theory of this, you should go and look at the book by Schroeder that's called Thermal Physics. Daniel Schroeder is the author. There's a chapter in there that almost every physics class skips, or it's the end of a chapter, but it gives a great amount of detail on how to apply the Gibbs free energy to understand these types of phase diagrams. It's a good resource. Okay, so in any case, what I wanted to say is that if we were to go into the liquid and then drop past this solidification line, or not solidification, past this line where we have the solid and liquid, what we would wind up with is a mess, okay? So that's the meaning of these vertical lines that terminate in a horizontal line. And then the horizontal line tells us, you know, which of the solid phases are in equilibrium with the liquid phase, which ones will emerge from that melt. Okay, other points that are useful. There's a point called a eutectic. You can come at this from the perspective of the Gibbs free energy, but I'm not going to try to do it right now. The main thing that I want to tell you here is that this is a place where, as a result of the balance between the free energies, the melting temperature reaches a minimum. For our purposes, you know, practical purposes, this is really useful because it means that there's a place where we can bring melting temperatures well below sometimes the natural melting temperature of elements that are present in a reaction. Right, so eutectics can be quite useful. All right, so that's a quick tour through binary chemical phase diagrams. So what I'm going to do now is to say a little bit about what we can do with this, besides having an idea of how things mix. And I'll give I think it's one example of an actual binary phase diagram. All right, so here we go. So here's another nice figure. This is taken from the ASM phase diagram database, which summarizes all of the known binary phase diagrams. This is for cerium and tin. And the reason I like to show this one is that it illustrates that in reality, these phase diagrams can have a lot of complexity in them. Some of them are incredibly simple. Some of them have a lot of complexity. So in this case, we can see that for cerium and tin, there are a large number of phases. Some of them are congruently melting. For example, this cerium 5-tin-3 melts at temperatures actually that are way larger than cerium or tin, but nonetheless produces this phase. So if we wanted to make cerium 5-tin-3, all we would really need to do is to heat this combination up above 1500 degrees C and then let it cool back down. Okay, but there's other phases that aren't like that. And let's see if I can find one. So cerium 3-tin, right? That very clearly is incongruently melting. And so in order to access this, we would either have to make the reaction at temperatures below the decomposition temperature, or carry out a different trick that I'm going to tell you about in just a second, which is essentially the principle of molten metal flux growth. Okay, so that's one way in which looking at a binary phase diagram before you do anything else can be really useful, right? You can know for sure that if I wanted something like cerium 3-tin, that I wouldn't be able to just make a direct melt. All right, so now it does raise an interesting question though. You know, is there a way other than just reacting powders to produce one of these incongruently melting phases? And the answer is yes, right? And that's illustrated here, where we can take advantage of the fact that when we're encountering one of these horizontal lines, what it implies is that above it, a liquid and a solid can be in equilibrium with each other. So for example, if we wanted to get this phase A2B, we could notice that there's a horizontal line connecting from about A equals 0 to A equals 33%, whatever it is. Okay, so you could make a combination of elements that are close to A2B, but have an excess of A. That's what this line represents. And how you would choose exactly how much excess A to have is unclear. But what I would say is that you would make a guess, right? Choose some value where you're in excess of this A2B. You would then heat this up into the liquid state at this concentration, and then allow it to decrease in temperature. Well, heat it up so that all the elements dissolve. This presumes that you have complete miscibility of the elements. But let's assume that they mix completely, that whatever they are dissolve into each other. And then we can decrease this temperature. And as we cross this phase boundary, the A2B phase will begin to form. Okay? As it forms, it'll deplete the melt of B, and we'll move more and more towards more and more A-rich melt. And as a result, you can just follow this line down to some point. And as you do this, crystals of A2B will form in the melt. Whether or not they will be large or small or twinned or whatever is going to be a question of how slowly you melt it and perhaps other conditions that we haven't really baked into this. But in an ideal, formulation here, by slowly cooling, we can drop out A2B and then ride this line all the way down to the eutectic. Okay. We could do the same thing for AB, right? We see that there's a horizontal line connecting here. Although, if we went too far, we might also, well, I think that if I were doing this experimentally, I'd be wondering if I'd be getting A2B and AB. I'd have to determine that, through the process. But if I wanted to completely eliminate that possibility of having A2B and AB, we could just make a decision to go over to the B-rich side and then carry out the same trick where we follow this line down. The only phase available is AB, and thus we have a very good expectation of only producing crystals of AB. Okay. Is there a question?
I'm just wondering if anyone has any questions at this point. Question? Yeah? Can you speak loudly though?
Okay, let's suppose that we choose A with like, how do you decide that it is always going in the left direction other than the right direction? Like suppose that we choose like A50% and B50%, and like then we go above the temperature, and how you choose like it's going on the left or right direction?
Did you get that right?
Can you say it again, JP?
So the question is, if let's say you start at AB, 50% in the melt, and you cool down a little bit, what determines whether it goes to the left or the right? Is that your question? Yeah.
Okay. So if you started at AB, let's say that you really had 50-50, there wouldn't be an opportunity for it to go left or right. It would form AB. And the reason is that that's the thermodynamically stable phase there. But if you were slightly to the left or slightly to the right, the situation would work a bit differently. So let's say that we're to the right. Well, I might confuse myself if I say we're to the right. Let's, but I'll try it. Okay, so let's say we're slightly to the right. The phase that's available is AB, right? But that AB can live or sort of coexist with the liquid mixture. So as we decrease temperature, some of the AB will come out. And your question is why? Right, so we're slightly off balance, right? We're slightly off balance. So what happens is as you go and let AB drop out, it's going to deplete the melt more rapidly of A than B. And as that happens, we're going to continue to move right in the phase diagram. The line, that I believe that one is called the liquidus line, will continue to drop, and that'll just keep happening until we reach the eutectic on the right-hand side. Did that answer the question?
I think this assumes if you were to follow the liquidus line slow enough that you
That's right. Yeah. If
you went too fast, you would end up.
That's right. If you go quickly through that liquidus line, you're going to wind up, not letting AB come out in a clean manner, and you really will end up with just a messy result.
Yep.
Yeah, I wanted to ask, when we are drawing like AB or AB out of excess of any one of the element, is this like how much excess we need, and is this specific to only flux growth or like for other types of growth as well?
Okay, can you just say that again to be sure I got it, JP?
So, okay, the question is, how do you determine how much excess of flux you would need? Let's say if it's AB, how much excess of A would be? And what was the second part?
Right, like this is for like, for example, for flux growth method, like for other kinds of growth, we can take the exact ratios.
Right, and does it apply to other types of growth other than flux growth?
Interesting. Well, so first of all, how do we choose the amount of excess? I know it's very normal to think about taking ratios of 1 to 20 or 1 to 100, something like that. Part of the reason why we do that is experience, right? It's kind of, this is very often in ternary spaces where we don't really know what the contours look like, but you can kind of presume that if you're using a flux that has a pretty low melting temperature, that as long as you stay in the regime where it's mostly that flux, then the melting temperature will stay low enough. Okay, but it doesn't really take advantage of this sort of detailed knowledge. So if I was trying to make, for example, let's see if I can get back to it, cerium-310, I'd have to make actually a more realistic decision about where I would go. I guess in that case, choosing something, I guess obviously in that case, choosing something that was very tin rich wouldn't get us there at all. It would only produce us cerium tin 3. So here's my answer. I'm kind of circling around it. If you have a detailed knowledge of what the binary or ternary phase diagram looks like, you can be very precise in terms of your ratios that you choose. And so here, if I wanted to make, cerium-310, I guess, I would just choose something. You have a lot of choices. You would just choose something less than 37%, right? And which concentration would really work the best might be something that comes from experiment, right? You might have to try several. And what was the second question? Sorry, JP.
Sorry, I'll just offer also that it depends on your experimental constraints. So perhaps temperature, the range of temperature you have access to, either the furnace you have could be a simple constraint, or maybe where you can raise the temperature of quartz up to, or some other crucible material you're using, would kind of limit where the range is. So for instance, on this right side, you see my mouse? Yeah. You have access to this whole liquidus line. So you could put 99% tin and try to get way down here in temperature, right? But then you have a very small range of growth. So that's one aspect. Where you can go way up here and start here and go really slowly and follow this, have this whole range of liquidus to fall down on and enable your growth very slowly. But that means you have to go quite high in temperature, 1200 degrees or higher to start. So somewhere in the middle, you just aim for that. And then finally, as Ryan said, these phase diagrams are never exact.
Oh boy.
There's data points on the space diagram, they're all lines, right? So they're usually a combination of experimental data and calculation. So they're not always right. Yeah. Ryan, the other question was, what other growth methods would this apply to?
Yeah, no, that's a good question. In some sense, if you're ever applying this, it's always a variation of a flux growth, right? It's a flux growth maybe is just an example of taking advantage of it's taking advantage of phase diagrams. I wonder if you might say that when you do a traveling solvent float zone furnace, that it's something like this, right? I think that's another example that is where you would be thinking about this sort of thing. Yeah.
Thank you.
Okay.
How am I for time, JP?
We have 15 minutes total or so.
Okay, that's fine. That's fine. All right. So here we go. We'll keep going. I wanted to make the comment that actually a lot of us are not focused on making binary phases, right? Although you might want to, but really, there's work that needs to be done for ternary and quaternary and so on. That's really difficult because we don't know what those phase diagram contours look like for the most part. But one idea of how to go about doing this is to think about isothermal slices amongst 3 elements. And that sort of thing you can look up sometimes, but if you can't, then you can go ahead and try to make diagrams that look like this, and then to make extrapolations in this space, in these types of spaces. And just for your reference, because it's fun, I wanted to show you this example of a ternary that is a combination of gallium, indium, and tin. Of course, gallium melts very close to room temperature, slightly above. But if you mix in a certain amount of indium and tin, it turns out that the melting temperature goes well below room temperature. And so just for anyone out there, I mean, first of all, we've played around with using this as a flux. Haven't found anything particularly important, but I think it's kind of interesting. And then this is a great alloy to bring to demos at elementary schools and things like that, right? There's other alloys that you're probably familiar with that are a bit like this, things like just solder flux, or not flux, just solder, or Woods metal or Fields metal, and so on and so forth, right? So these sorts of things are interesting to look at and can be pretty useful in some contexts. All right, so that's phase diagrams. There is so much more to say about them, but what I want to do now is to just move on to growth techniques. And we've considered a few features of combinations of elements or compounds. And you can see that when you look at these things, it can help to guide you towards making a decision about how you would actually grow something. And here I've gathered together most of the crystal growth techniques, at least in terms of broad categories. I'm sure you could think of others where we have things like solution growths. That's molten metal flux, perhaps also traveling solvent floating zone could be included in there. We have vapor phase growths. I won't touch on that today, but I hope someone else will talk about that. Thin films, of course, 2D layers and stacking, and then melt growths, right? So what I'll do for the rest of this talk is just say a little bit more about molten metal growths and then direct melts. And I want to emphasize that, well, I'll go to direct melts first. And I want to emphasize that direct melts are really only applicable or useful when we're talking about congruently melting phases. And so a direct melt, in my mind, is really just any technique where we're going to heat something to a high enough temperature that it melts, and then we're going to crystallize the phase directly out of the melt. And the entire question then is practical, right? It's how are we going to melt it? How are we going to get it that hot? How are we going to control the cooling? How are we going to control the shape of the crystal as it comes out of the melt? Those sorts of questions. And that all comes down to methods like this, where you can use resistive furnaces or arc furnaces or induction furnaces. And then after you come up with the way that you're going to heat them, you may set up some sort of an apparatus to control the object as it cools. And a good example of this is Czochralski, which is where you insert a pull rod into a melt and then slowly withdraw it from the melt. And as that happens, there's an interface between the solid and the liquid where your crystal is forming. Okay, so let me say some things about some of these. Oh, and just to emphasize, it's no good for incongruently melting phases to think about these methods very much. All right, so the first one of these, which I think you'll see in your demos, it's very powerful. It's one of the best ways to reach the very highest temperatures in a lab. And it's just the example of arc melting. And an arc melter is shown schematically here, where you really just have a welding power supply that's in this yellow box. You have some cooling water to prevent your experiment from melting your apparatus. And then you have some sort of enclosure for gas handling. And what happens is that you have the power supply connected to an electrode that you can discharge the electrical arc through. You typically discharge it through an inert gas like argon. That electrical arc will be driven through your sample and then exits through a hearth, right? It's usually a big piece of copper that's water cooled. And by doing this, you can really produce some incredibly high temperatures. And just to demonstrate that, here's a quick video. This is a piece of zirconium. Is the video playing, by the way?
Yeah.
Okay, so we strike the arc, bring it onto the zirconium. Zirconium melts at about 1800 degrees C, so well above what you can reach in a normal resistive furnace. And as you can see, within seconds, the arc is able to heat this past the melting temperature. I especially like this one because the metal flows down into the pit. It's normal in an arc furnace to have some pits like this because it allows you to encourage elements that you're reacting to flow together and thereby mix in the way that.
Oops.
Here is that when you turn the arc off, that flash was just the camera changing its darkness. But you can see how quickly this cools, right? So it's an incredibly good way to reach high temperatures, in a safe environment. But what is completely uncontrolled here is the cooling rate. And that cooling rate is really very fast. So generally speaking, your expectation would be that you can access a congruently melting phase, but that you would not produce large single crystals. Okay, you're probably going to produce polycrystals out of this. But one additional hint is that for some materials, even though it's a polycrystal, you can cleave out appreciably sized grains that sometimes are effectively single crystals and are reasonably high quality. So that's one way to, sort of a poor man's way of obtaining single crystals of materials that form at really high temperatures. One word of warning. This technique involves going to very high temperatures very quickly. This is not well suited to elements that have high vapor pressures, right? So if you wanted to arc melt a piece of sulfur, that would be a really bad idea. Even aluminum, right? If you arc melt aluminum, it'll evaporate pretty quickly. Feel like I had one more thing to say about this, but it's not coming to me. In any case, you have to think about sort of the personality of the elements that you're dealing with when you set out to arc melt something, in addition to the phase diagram. Okay, maybe my other thoughts are here. All right, so I mentioned a lot of this already. Arc melting has some other nice applications that I want to mention. For one thing, if you start off with a powder of something, it's a good way to partially clean it up. An example of that is shown on the right-hand side here. I actually now don't remember what this is, but it's a powder of some metal. We arc melted it and produced this nice little ball. And what you can see is that surrounding the ball is a pattern of sort of dirty junk. That's all dirty junk that was in the powder. So by arc melting it, at least we drove that off. What else can we do? We can make crucibles. Shown beneath here is a tantalum tube. Sometimes when you need to go to very high temperatures, above the melting temperature of quartz, you may want to use a sealed tantalum tube. The reason for that is that it doesn't react with a large number of elements, and its melting temperature is very high. I forget what it is now, 2400 C or something like that. Right, so we can make crucibles by welding tubes together. That's a useful technique. Of course, the one thing I didn't say that's important to know is that if you want to arc melt something, it has to be something that has electrons that are available to move around inside of it. In other words, directly arc melting something like silicon or germanium or boron is going to be unsuccessful. And so you do have to think about that aspect of your materials in the first place as well. Okay, what other types of direct melts are available to us? Well, another thing that I think is very nice is induction furnace heating. That's summarized here schematically. The idea is that if you have a RF generator as a power supply, you can put that RF current into a coil. A current will drive around the coil. That'll produce a magnetic field along the axis that's oscillating back and forth. And then if you put a workpiece like that tantalum crucible into the coil, electrons within it will be accelerated around. That will resistively heat the material, and it'll do it very locally. So this is a really great way to accomplish very rapid localized heating. And that heat will, of course, be transmitted into whatever material you put inside of the crucible. And if that material is metallic, it'll also couple to the magnetic field. All right, so in this way, you can have good control over how you're heating something. And what's more, you can easily reach decently high temperatures, certainly higher than what you can reach in a normal silicon carbide heating element, resistive furnace. Those tend to max out around 1500. Ones that you might buy from MTI, the company, it's more typical to have 11 or 1200. If with our induction furnace, we sort of routinely go to something like 1700 degrees C. So it's a powerful technique, a good way to create direct melts. Okay, I don't have enough time, so I'm not going to show the video here. But the other thing that's really intriguing about this is that there's also a levitation capability, right? Because we're talking about a magnetic field. So you can lift a sample potentially. It gives you a way to do crucible-less growths, which might be advantageous if you're worried about getting impurities into your samples that are taken from the crucible itself. Okay, one last comment on direct melts. We can think about different ways of heating materials. Of course, there's a lot of ways to do that. The other aspect of this is how do we let it solidify? And one of the most well-known versions of controlling solidification is what's called the Czochralski crystal pulling process. In this case, we're using an induction furnace to heat a crucible. This was a graphite crucible, which couples very nicely to a magnetic field. Inside of it, we have a melt. I think this one was just silicon. And then we're inserting a pull rod into that melt. By getting a crystal to nucleate on the end of this, we can then slowly withdraw the pull rod. And as this happens, more and more of the silicon will attach itself to the solidified part. And if we do this right, it'll happen in a very orderly manner, producing a large single crystal. And this is probably, one of the most common ways of producing large crystals, for example, for neutron scattering. Okay, so, and you can imagine other ways to control the solidification process. Really, the limit is just the amount of creativity that you have for setting up an apparatus. Okay, now just briefly say something about flux growths. And hopefully another speaker will be saying more about this. So again, to do flux growth, we want to take advantage of these horizontal lines, right? Just to give you an idea for a very interesting demo that you can do on your own to illustrate this to yourself, what this can be, to visualize it, you could do something like dissolve sugar or borax into water. And that's what's shown here. Okay, but in practice, we're not interested in growing borax. What we want to grow are intermetallic quantum materials. And so, you know, at the beginning of any attempt to grow one phase like this, you know, like the question earlier referred to, we have to think about this flux. And we don't just need to think about what concentration, but we also need to think about what flux might be useful. And there are many, many choices available to us. Some of them will be reactive fluxes, meaning that the element that the flux is made out of can become part of the crystal. Some of them are non-reactive fluxes, meaning that it's just an environment where the crystals would form. And here's some examples. It can be more or less anything you can imagine, right? But some of the usual suspects are salts, aluminum, gallium, indium, zinc, antimony, bismuth, and then you can go beyond that and think about binary eutectic mixtures. You can even push this further and think about hydrothermal situations. I've seen cases where people used oils, you know, more or less anything where you can get one substance to dissolve into another. All right, so what is the idea here? And I promise I'm almost done. Well, what we're gonna do is to take our elements in a ratio where we think we're gonna be able to create a melt. You'll very often need to put them inside of a crucible. Here we have aluminum oxide crucibles, but there's many others to be considered. A standard thing to do then is to place these inside of a quartz tube. The reason for this is that when we heat elements up to high temperatures, if we just do that in air, it's very likely they're going to interact with air and produce something that we don't want, right? So you want a convenient way to protect them, and a convenient way to do that is to seal them inside of quartz tubes. I want to make an aside here and say that this last summer, when I arrived at UC Santa Cruz, I had none of my equipment working. I didn't even have a hydrogen oxygen torch, which is what you normally need to do this. So what we decided to do was to see if we could do flux growths in Pyrex tubes, which has a much, much, much lower melting temperature. We did that, and we looked at binary phase diagrams and limited all of our growths to below 300 degrees C because Pyrex starts to soften around 400. And sure enough, it worked just fine. There are many materials that you can grow in the absence of quartz. I think it's just an interesting side note. And the other thing that I want to tell you about that is that if you work in a lab that has been around for a long time, it may have both quartz and Pyrex in it. Probably someone in the demos will show you this, but you can always tell the difference between Pyrex and quartz by looking down the axis of the tube. The Pyrex is going to look green and the quartz is going to look white. So always be on the lookout. Don't get those two things mixed up. Okay, in any case, we can work the quartz, creating an ampoule that's sealed under vacuum, right? We can detach it and seal it up using a torch, like a hydrogen oxygen torch. This will then go into a furnace where it will go through a heating cycle that allows us to control the way that we go through the liquidus line, like we discussed earlier. The way that you choose these rates is a matter of substantial conversation. You know, what you'll see very often is, oh, this growth took 2 weeks. And you'll think, oh, well, that's just because it makes sense. It needs to take 2 weeks. But what I would encourage you to think about is whether or not this really makes sense. In my experience, there are some types of flux growth that you can do very quickly. And sometimes this 2 weeks or 3 weeks or whatever is some sort of inherited artifact from the past, right? Maybe someone went on vacation for 2 weeks and the growth worked. So do be thoughtful about that. It's not necessarily true that all growths need to take that long. In any case, you choose a heating cycle. At the end of it, you need to separate your crystals from the flux. So what you'll do is to take this out of the furnace while you still have a liquid phase. You place that inside of a centrifuge. And then because the crucible itself has this little separating layer that has holes in it, or maybe it's a piece of quartz wool, by placing this in the centrifuge and spinning it, you'll be able to move the liquid away from the solid. There are all sorts of safety considerations to think about prior to doing this. And there are too many to enumerate right now, but I just want to emphasize that this is a step where you do need to be thoughtful about how you're doing it and make a plan well in advance. And if you're not experienced with this, work with someone who knows what they're doing. Okay, and then finally, at the end, you're very likely to produce crystals. And what's so fantastic about crystals produced in this way is that they very often reveal their crystallographic directions because the shape of the crystal reflects the underlying symmetry of the crystalline lattice. The other thing that is very exciting about this method is that because we don't know what ternary phase diagrams look like in detail, there is always the possibility that you will turn up a phase that you didn't intend to find, and it may even be something that hasn't been discovered before. I think that's really exciting. All right, so that brings me to the end. I hope I was able to cover some useful topics. I want to just conclude by saying that, of course, this is really just the first step, right? So the loop that we're all actually pursuing is one that goes make, measure, and tune. When we think about crystal growth, we're really just thinking about the first step. And to quote Winston Churchill, who knows if that's appropriate or not, but here we go. This is not the end. It's not even the beginning of the end, but it is perhaps the end of the beginning. So I guess I'll end now and say good luck in all of your crystal growth activities. All right, thanks, JP.
Thank you. Okay, we have time for a couple questions. Yeah.
I'm wondering, can arc melt be used to get some high temperature phases since you are essentially ion chains with fossils?
Sorry, can arc melting be used to obtain high temperature phases?
Yes, it's essentially quenching the compound.
It's okay. The question is, when you arc melt, you access the high temperature phase, but are you concerned about just quenching the melt rather than actually forming crystalline phase?
Yeah. No, that's a reasonable question. So first of all, as long as you are at a congruently melting phase and your stoichiometry is right on, it's going to form that phase. In that case, it's more of a question of how polycrystalline will it be, right? Like it could be that it will be extremely polycrystalline. I've also seen cases where the grain formation is really fast, and you can cleave out what are single crystal pieces. They're small, but you know it's a single crystal piece. I suppose a different consideration that might matter for some materials is if it did undergo some sort of a structural phase transition. You know, steels do a martensitic phase transition. And it does matter exactly how you heat treat them. So I suppose if you were at a congruently melting phase and there was an additional structural phase transition below it, you know, within the solid, then the rate at which you cooled through it could matter a lot. But that would be some sort of a special case. Does that get at the question?
Yeah, thank you. Yes.
Thank you so much for the nice presentation. So, so you told that initially for boron-based or carbon-based compound, we need to follow certain strategy. So if I need to grow a binary compounds which contains boron, so what is the method or what is the right flux for that?
Can you say that one again, JP?
So you mentioned about boron and carbon special methods. So if you want to do a flux growth with boron, for example.
Yeah. Yes. Okay. Very difficult. Boron is a giant pain, but a few recommendations. One is that aluminum is kind of a go-to flux. You can't get a lot of boron into aluminum, but if you make a very large amount of, like, make the ratio be mostly aluminum, 100 aluminum to 1 boron, then you can do that. And that's something that people have done for hexaborides and dodecaborides, you know, for a long time. Of course, the problem there is, as far as I understand, is that you also often, and this is true for any flux growth, by the way, you will run into some cases where your flux inclusions create problems for you, right? And that's been an ongoing problem for borides grown in an aluminum flux. I looked into this years ago for the hexaborides, and I think that the other thing that I concluded could be useful for boron is iron. I think that boron goes into iron reasonably well. And the main problem there is that the melting temperature of iron is pretty high. I think it's like 1500 degrees C. So maybe you could imagine, okay, here's a suggestion. If you wanted to use, like, let's say you could identify an element where boron or carbon had a good solubility, but the melting temperature was high, you might then look into what other elements would bring the melting temperature of the iron down, right? Like, look for a nearby eutectic that allows you to keep mostly iron, but a little bit of something else. You know, a melt like that might accommodate boron pretty well. And then what about carbon? I don't remember off the top of my head, but what I can tell you is that chemists like Susan Laturner, have worked on that sort of problem. And so I would just refer you to her papers. Maybe someone like Kenneth Zetas has also published some things about that. I would look to our chemistry friends and see what sorts of, what sorts of exotic things have they been trying.
Sounds good. Thank you.
Yes. When you're doing an induction melt, how do you know what temperature you're actually at inside the crucible?
Yeah, good question. So there's two approaches. The first of these is to use a pyrometer. Okay, pyrometer is not so bad. All this is a camera that measures the black body radiation and then converts that to a temperature. That works reasonably well, except for the fact that the light is traveling through something, right? There's always a enclosure of some sort, and very often that's quartz. So there's a correction factor, and you have to characterize that before you start. How would you characterize that? One way would just be to melt some standards, right? And measure it as you go. Then you can get an idea, oh, it's a 10% correction factor or something like that. But a different thing that you can do, and it also works reasonably well, is to just make sure that your enclosure has a thermocouple feed through. That sort of thing is very standard. You can buy it from like Kurt J. Lesker, something like that. And just run a thermocouple up to where your crucible is. And then your main problem is just figuring out how to reliably couple it to the crucible. And then you might say, well, wouldn't you induce some currents in your thermocouple wire? And the answer is just make sure that you don't make a loop, right? Don't make a loop that's perpendicular to the magnetic field, and you'll be fine.
Okay, any final question? Yeah, please.
Yeah, another question. You said that a lot of these phase diagrams are actually calculated, they don't have data points. If we have, say, a 2 or even a 3 element phase system we need, is there a way we can calculate one for ourselves?
I don't know the answer to that question. I've wondered the same thing myself. I wonder why that's not routine. And I don't strictly know the answer to it. Maybe it's hard. I presume that in order to do this, there's some sort of DFT calculation. I don't know. I don't know. Maybe if you go online to one of these resources like what's it called? The Materials Data Project or something. There are resources online that will do calculations for you. So there may be a path there. But I actually don't know much about that. Yeah, sorry, that's an unsatisfying question, but I really don't know the answer to that.
I think there may be packages you can download. But
Yeah.
it's like DFT where you would need some knowledge on how to use it, what you're doing. It's not
And I just think that if it were easy, we'd be seeing a lot of it because inorganic chemists, think about this sort of thing. It's kind of their bread and butter, but it's not just commonplace. And I don't know why it's not commonplace.
Okay, Ryan, we have to get going on our training, so thanks very much.
All right. Yeah, thanks everyone. Feel free to reach out.
All right.
All right, sign off.